Neural networks require large amounts of training data. Given a task, for example object detection, we need to get accurately labeled training data. Simulation has evolved a lot in the recent years. Photorealistic renders are now capable of generating realistic images. These can be used to generate training data for neural networks. Simulation requires setting many parameters like object and scene properties, for example, object shapes, colors, locations, and materials, lighting, etc. These are generally set by human experts. But this manual synthetic data generation needs significant human effort. Furthermore, it is expensive and the data generated can be suboptimal. So, can we come up with an alternative to manual synthetic data generation? In this work, we optimize the parameters of the simulator. We learn these parameters to directly maximize accuracy on a computer vision task like object detection. We propose an end-to-end algorithm for optimizing the simulators. The problem of finding optimal simulator parameters can be formulated as the bi-level optimization problem. Data is generated from a simulator with parameters psi. The data is used to train a neural network with parameters theta, and the objective is that this trained network should perform well on a real-world task where the validation loss is denoted as LVAL. Here, theta hat of psi denotes the neural network parameters after training on data from simulators psi. Equations 1a and 1b represent a bi-level optimization problem. Computing the gradient of the bi-level objective is difficult as simulator can be non-differentiable and backpropagating through neural network training is impracticable. In this work, we propose differentiable approximations for the non-differentiable bi-level objective. This graph shows theta on x-axis and the neural network loss on y-axis. Our objective is to minimize LVAL with respect to psi. So we initialize psi to some value psi t. The neural network trained on this psi is theta hat of psi of t. The blue curve shows the loss on the validation dataset as a function of neural network parameters. Our aim is to move in a direction such that the objective decreases the maximum. We take a linear approximation of the objective at the current point, shown in the black line. The approximate value of objective at some point psi t plus delta psi can be written as equation 2, where delta theta is given by this equation. How do we find this delta theta? To be able to minimize this approximation, we need the value of delta theta. It can be seen in the graph that delta theta is the difference between the two theta hats. Next, we see how to approximate this delta theta. It can be seen that theta hat of psi t is the optimal neural network parameters we get upon training it on data from simulator psi. That is, it is the minimum of L train of psi t, which is shown in the red curve. Similarly, theta hat of psi t plus delta psi is the minimum of L train of psi t plus delta psi, which is shown in the red curve as well. Next, we take a quadratic Taylor expansion of L train of psi t plus delta psi around current theta hat psi t, which is shown in the black curve. We use the minimum of the quadratic approximation to approximate delta theta. This minimum is shown by thick black dotted line. Now we put this back into equation 2, which gives us the following equation. This can be seen as the differentiable approximation of our objective. It can also be written as the following. So it can be seen that now we have written a differentiable approximation of our objective and its derivative. But in the derivative term, how do we calculate the gradient of expectation? Also, how do we find the Hessian inverse into gradient term? More details about these two terms are presented in the paper. Overall, the final derivative formula can be written as this, and the equation for optimizing simulator can be written as this in the form of a single gradient update step. Overall, the optimization is done in an iterative manner, which requires solving approximate conjugate gradient descent at each step. We perform extensive evaluation of our method. We optimize a state-of-the-art photorealistic renderer Arnold, which is non-differentiable, to perform object detection on a real-world dataset LMO. The proposed method is up to 50 times faster than the current state of the art. This is a significant speed up, and it is much more accurate. It gives 8.5% higher accuracy in terms of MAP for object detection. Again, this is a significant increase. Furthermore, the method requires much lesser data generation as compared to the state-of-art methods like LTS, which is learning to simulate, or random search and Bayesian optimization. In these images, we show the object detection results on the LMO dataset. These results are using a neural network which is trained entirely on synthetic data generated by our optimized Arnold renderer. Thank you.